right, so here we go, section 2.5. Matrix inverses. The objectives in this section are to identify what is an identity matrix, how to find the multiplicative inverse matrix, which we'll just call the inverse matrix, and then to use that inverse matrix to solve systems. Right? All right, so some language, some terminology. I'm going to be using the phrase identity matrix or the identity a few times. The identity matrix, by definition, is a square matrix with ones on the main diagonal and zeros in all other places. Now, the identity matrix comes in different sizes. This is a 2 by 2 identity matrix. Ones on the main diagonal and zeros everywhere else. If we get a little bigger, we could have a 3 by 3 identity matrix. Ones in the main diagonal and zeros everywhere else, right? We can have a 4 by 4 identity matrix where we have ones in the main diagonal and a whole bunch of zeros everywhere else. 4 by 4 isn't the biggest. They could go bigger. They could be a 5 by 5, a 6 by 6, but they do always have to be square, and it will always work out because they're square that the ones in the main diagonal and a whole bunch of other zeros. Okay? All right, so let's take a look at what's going on here. What is the purpose of an identity? What does an identity do? Well, in mathematics, the purpose of identity is to do nothing. Under the operations that have identities, the identity is the value for that operation that does nothing. For example, what's 3 plus 0? Well, 3 plus 0 is just 3 because adding 0 does nothing. So then we would say that under addition, that the additive identity is the number 0. It's the thing that you can add and it does nothing. Okay? Multiplying by 1 does nothing. Like, what's 3 times 1? 3 times 1 is 1. So that means that under multiplication, the multiplicative identity is 1. The identity matrix does the same thing, it just does it for matrices. The identity matrix is the matrix that when you multiply it, it doesn't do anything. So if I were to take this matrix and I were to do the old school by hand multiplication, this is a 2 by 2, this is a 2 by 2, a 2 by 2 times a 2 by 2. These match, so I can do the multiplication. The answer is also going to be a 2 by 2, so when I have an answer, my first entry is going to be the first row times the first column. So that's going to be 5 times 1 plus 3 times 0. 5 times 1 plus 3 times 0 is 5. And then when I do the first row times the second column, I'm going to get 5 times 0 is 0. 3 times 1 is 3, so I get a 3 right there. And then when I do the second row times the first column, negative 4 times 1 is negative 4. 2 times 0 is 0, so I get a negative 4 here. And then when I do the second row times that second column, I get a negative 4 times 0, which is 0, and I get a 2 times 1, which is 2, and so I'm back to here, and I'm back to where I started because the identity for matrix multiplication does nothing. Now this is multiplication on the right. What if I multiplied on the left? Would it still do nothing? Let's check and see. First row, first column, I'm going to have 1 times 5 is 5 plus 0 times 4, 5. First row, second column, I have 1 times 3 and 0 times 2. Well, 1 times 3 is 3 and 0 times 2 is 0. Second row, first column, 0 times 5 plus 1 times negative 4. And second row, second column, 0 times 3 and 1 times 2. 5, 3, 4, 2. Okay. The identity matrix is the matrix that when you multiply, it does nothing. All right. So why do we care about identities in general? Why do we care about identity matrices? Well, the simple answer is algebra. When you first started solving algebraic equations and someone handed you something like this and asked you to solve it, you would say, I am going to subtract 2 from both sides And then you draw your line. You say that means x is equal to 2 because you did 4 minus 2, and 2 plus negative 2 is 0. Now, the reason that this works is because of identities. Because these two numbers right here are opposites, and when added together, we arrive at that additive identity. So the negative 2 here is the additive inverse and when you take a number and add it to its additive inverse, you get the additive identity, which is what we want because we want to isolate x, and x plus 0 is just x, which is why this works. And then when your math got a little bit harder, you started doing things like this. 3 times x equals 12, and then your job was to solve that. And so you'd say you divide by 3, but technically what you're really doing is you multiply both sides by 1/3. And the 3 times the 1/3, well, under multiplication, 1/3 is the multiplicative inverse. And when you multiply a number, in this case 3, by its multiplicative inverse, the answer that you get is the multiplicative identity, or 1x. But we never write the 1, right? And then 1/3 times 12 would be 4. And then we've got our solution to our algebra. And then if you did something even more complicated, like let's say you had 5x plus 2 equals 12. Now you would just make use of the additive identity, and then you'd make use of the multiplicative identity, and you come up with a solution. So we're going to use those same things, those same multiplicative and additive concepts, just with matrices. Okay? So we're going to find the multiplicative inverse of a matrix. And the multiplicative inverse of the matrix is whatever matrix that you can either multiply by on the left or on the right and get the identity, right? Multiplicative inverse. So 4 times 1/4 is equal to 1/4 times 4 is equal to 1. Multiplicative inverses on the left or on the right, you get the identity. Same thing with matrices. Right? Here are two matrices, A and B, and my job is to verify that these matrices are inverses of each other. Well, if these two matrices are inverses of each other, when I do this or when I do this, I should get the identity matrix both ways. Right? Now I got a bunch of space here, so I'm actually going to do this one by hand, but you absolutely could perform this multiplication on the calculator. I'm just going to do this one by hand because sometimes it's just fun to do these by hand. So there's my A, there's my B. I'm going to do A times B first. Okay, so this is going to be A times B, and then over here I'll do B times A. Okay? So let's see. 1 times -5 is -5, plus 3 times 2 is 6. First row, second column. 1 times 3 is 3, plus 3 times -1 is a -3. Second row, first column. 2 times -5 is -10. 5 times 2 is 10. Second row, second column. 2 times 3 is 6. 5 times -1 is -5. Add, see what we get. -5 plus 6 is 1. 3 plus -3 is 0. That should be 10. -10 plus 10 is 0, and 6 plus -5 is +1. We got the identity. So it looks like A times B gives me identity, but now I'll check B times A. -5, 3, 2, -1, multiplied by 1, 3, 2, 5. So let's see. -5 times 1 is -5, plus 3 times 2 is 6. First row, second column. Negative 5 times 3 is negative 15, plus 3 times 5 is positive 15. Second row, first column, 2 times 1 is 2, and then negative 1 times 2 is negative 2. And then second row, second column, 2 times 3 is 6, negative 1 times 5 is negative 5. Add, 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 and what do we get? Let's see, negative 5 plus 6 is 1, negative 15 plus 15 is 0, negative 2 plus 2 is 0, and 6 plus negative 5 is 1. So we get the identity that way too. That means that those two matrices are inverses of each other. Do you see where this is going? It's going back to here. It's going back to solving systems of equations and solving equations using matrices. That's what we're going to do. Okay? All right, so first off, I need to be able to find a matrix inverse. I need to be able to find the multiplicative inverse of a matrix. And here are the steps for doing it. Form the augmented matrix A augmented with the identity matrix. Perform row operations to turn AI into IB, if possible, and then B is the inverse of the matrix. All right, so step 1, form that augmented matrix. That augmented matrix to A would be 1, 3, negative 1, 2, augmented with 1, 0, 0, 1. And now I'm going to perform row operations to turn this side into the other side. Meaning I'm going to do whatever it takes to do to turn that 1, 3, negative 1, 2 into 1, 0, 0, 1. And I could do this, and this is the traditional way of doing this, but I'm going to make an argument that this is not efficient, and because it's not efficient, that's not how I'm going to do it. I'm going to make the following argument, that I am going to use my calculator to find my inverses of matrices. So I'm going to pause the video and find that calculator. So well, you know, I found my calculator, and I'm going to find the inverse of this matrix using my calculator. So I'm going to go over here to my calculator, I'm going to go to my matrix menu, and the first thing I'm going to do is I'm going to type in that matrix A. So I'm going to edit it. It is a 2 by 2 matrix. The entries are 1, 3, negative 1, 2. Quit out of there, and then I'm going to say, find me the inverse of that matrix. And I'll write it as fractions. And so the inverse of that matrix is the matrix 2/5, negative 3/5, 1/5, and 1/5. And if I had done all that work by hand, I'd end up right there too. Should I go through that again? Because what I did is I just did this on the matrix, on the calculator. I just found the name of the matrix and raised it to the negative 1. The negative 1 is this key right here. I don't know if you can see my cursor. I just flashed. It's red there. That's the inverse key. See? And if I take the inverse of the inverse, I get back to where I started. And if I take the inverse again, and inverse again, and back to where I started, matrix inverses. The inverse of the inverse is the inverse, is original matrix. Okay? So how am I going to use this to solve a system? Well, I'm going to solve the system by using the following algebraic logic. Here is the algebraic logic. I am going to take this system and rewrite this as a matrix equation. So here's how it's going to look as a matrix equation. 2, negative 3, 1, 5. We're going to call that matrix A. Multiplied by matrix X, Y. And we're going to call that matrix big X, or the variable matrix. And A is being multiplied by X. And then we're going to say that this is equal to the matrix 4, 2. And we're going to call that matrix B. And so we have the equation A times X is equal to B. Now, if I want just X, if I want to make the A go away, because I don't want a times x, I just want x. How do I make the a go away? Well, if this was algebra, you'd say divide. But there is no such thing as division when it comes to matrices. So what we're going to have to do is we're going to have to use a different technique to make it go away. And that technique is we're going to multiply by the inverse. So if I were to multiply on the left by the inverse of a, then I would do the same thing to the right-hand side of the equation. I multiply on the left by matrix A inverse. So I'm multiplying on the left by matrix A inverse in both places. Then these two, when I multiply them together, they give me the identity matrix. And the identity matrix doesn't do anything, so I can essentially just not even have to write it, and I just get x. And then this becomes my solution or my answer for my system. Right? So that's what I'm going to do. But I'm going to do it all in the calculator. And I'm just going to simply say that x is equal to, and then I'm going to go over to the calculator and let the calculator do all the work. First things first, put those matrices in. Matrix A is the matrix that is a 2 by 2 matrix, and it's the matrix 2, -3, 1, 5. And then I'll quit, and then I'll go back to matrices, over to edit, down to matrix B, and I'll put in that matrix B, which is a 2 by 1 matrix, and those entries are 4 and 2. And now I need to type this into my calculator. I need to tell my calculator to do A inverse times B. So matrix A inverse times matrix B. And I get 2, 0. So I come back over here and say that x is equal to 2, 0. But what was x again? Oh, that means that that's equal to the matrix xy. Or in terms of the original problem, x is 2 and y is 0. And that's my solution to my system. Let's try it again. Where are we at in terms of time? We're at 17 minutes. All right, so I'm going to pause the video or stop the video. I'll come back and do this next one in the next part 2.